Okay, we're in the Lightboard studio. We want to go over an example using force analysis to solve a particular problem. So what I've got here is I've got a block on a ramp. So the inclination of the ramp is 30 degrees. My block has a mass of 2 kilograms, and the coefficient of static friction between my block and the ramp is 0.5. And so I've got this setup here, and what I want to figure out is how much friction is required here to keep this block in equilibrium, at rest, and staying at rest. So I want to figure out how much friction is necessary for this to happen. All right, so I've got my picture. I'm going to immediately draw a free body diagram. And so I'm going to do that. I'm going to start over here. And I'm going to pick my axes so that they more or less align with the ramp. So my x-axis here is pointing down the ramp, the positive direction towards the bottom of the ramp. And my y-axis is perpendicular to the ramp. And then I'm going to place my block right at the center. So what forces do I have acting on my block? Well, of course, I've got the weight down. Then I've got a normal force perpendicular to the ramp. And of course, this can't be everything, all of the forces that are acting on my block. If this was the case, then the block could not possibly be in equilibrium. The block would accelerate down the ramp because there's a net force down the ramp right now. So I'm going to add in a third force, and that's where static friction is going to come in. So it will be the static friction force that keeps this block at rest on the ramp as opposed to accelerating down the ramp. So the goal here is we're trying to figure out how much friction is required for this block to stay in equilibrium. And so the one thing I want to point out here is our ramp is at 30 degrees. So that means this angle right here is 30 degrees. So remember, when we start our free body diagram, if we have any forces that aren't along the x or y axis only, we should do a second free body diagram that breaks up those forces into the components. And so I'm gonna do that here. So most of the free body diagram looks exactly the same. I've still got the normal. I've still got the friction force up the ramp. But now I'm going to draw the component of the weight down the ramp, which again, if you look up here at this picture, that would be the magnitude of the weight times the sine of 30 degrees. And then I've also got the component of the weight perpendicular to the ramp, so that's weight y. And that's the magnitude of the weight, it's actually in the downward direction, so I'm going to add the minus sign, cosine 30 degrees. So now I've got all of my forces pointing along the x or y axis in my coordinate system. And so at this point, I'm ready to take my free body diagram and leverage Newton's second law. So remember Newton's second law, F net in the x direction equals max, and F net in the y direction equals may. Right? Vector equation, so it's actually multiple equations in one. And so what we're interested in here is how much friction is required to keep this object at rest. And so I'm going to focus at the moment on this expression. So F net in the x, well, I've got plus the weight times sine of 30 degrees down the ramp, and that's my plus direction. And then I've got in the opposite direction the friction force. Now notice what I've done here. I have removed the vector signs and I have included plus or minus when I'm putting the magnitude of the force up there. So the plus or the minus is my direction here, because again, this is just along the x-axis. So now I'm doing 1D. So I've got my two forces. That's all I've got on my free body diagram. This has to add up to m AX. And remember, the whole premise of this problem is we want the object to stay at rest. So that means the acceleration is 0. And so the static friction force that I need for this block to stay at rest is the weight times the sine of 30 degrees. Well, remember, the weight is mg, so sine of 30 degrees. And in this case, my mass was 2 kilograms. G is 9.8 meter per second squared. Sine 30 is 1/2. And so this is going to work out to be 9.8 newtons of force. That's the amount of static friction that I need to keep this object at rest. Now, the most obvious question to ask next is it possible for static friction to provide 9.8 newtons of force, or is this inherently an unstable setup? Will the block just slide down the ramp? So the question is, can the surface between our ramp and our block, can that, those two surfaces, can that generate 9.8 newtons of friction, or is the maximum value something less than that? And if you recall, the maximum value for static friction, let's put it right here, Fs max is mu s times the normal force. So mu s, that's the coefficient of static friction. I was given that at the start of the problem. It's 0.5. And so what I want to do is I want to figure out what is the normal force in this problem. I'm going to multiply that by 0.5. That's going to give me Fs max, and then I'll compare that to the amount of friction that is necessary. If Fs max is larger than the amount of friction necessary, then we're fine. The object's going to stay at rest. If Fs max is less than the 9.8 newtons, then the block, when I set it there, is actually just going to start sliding down the ramp. So how do we figure out the normal force? Well, that's where we're going to come back and look at the y analysis. So net force in the y direction, I've got the normal force up, so plus the normal. I've got the y component of the weight down, so that is mg cosine 30 degrees. And this has got to add up to be may, which equals 0, because we're not accelerating into the ramp or off of the ramp. We're going to stay on the ramp, no matter whether we stay at rest or slide up or down the ramp. So this tells us that the normal force has got to be mg cosine 30 degrees. So let's see if we can do that in our heads. I think it's about 17 or so, maybe 18 newtons. So this is what my normal force is equal to. I bring that back over here, so Fs max for this surface, 0.5 times that 17 newtons. So that gives us about 8.5 newtons for the maximum friction force that can be generated between these two surfaces. So that's the maximum amount. We look at how much is required for this to stay in equilibrium, and we immediately recognize there's too much force required for this to stay in equilibrium. This block is going to accelerate down the ramp, right? There's going to be a net force down the ramp. So what's a way to get around this if you were trying to set up a stable situation? Well, you would either need a larger coefficient of friction between the surfaces, so use different surfaces, or use a shallower ramp. So something like 20 degrees or 10 degrees, then placing this 2 kilogram block on the ramp would result in it staying there. All right, so this is a nice little demo on, we've got a word problem or a picture problem. We've got to do a free body diagram. We've got to break all of our forces on the free body diagram up into the components along the x and the y axis. Then we leverage Newton's second law. The first question I asked is how much static friction is required. Then I compared that to how much is actually possible in this particular setup. And the conclusion that we draw is that in this case, the block will not stay at rest on the ramp. It will actually accelerate down the ramp. All right.